we're gonna talk about more on reactions because in our previous class, we talked about number one, how to make or name a compounds. And we said that there are three different classifications of the compound. If you can identify which that compound and where it belongs to, then you're already one uh, step ahead. Okay. So then once you know how to name the compounds, then we need to know how to do some calculations that is quantify it basically. So if you have a cup of water, by looking at the volume, you'll be able to calculate the weight or how much the mass of the water is present in your cup. And from there, you can do a conversion of figuring out how many molecules, individual water molecules is present. Or if you want to identify the number of elements there are, you could be able to figure out how many hydrogen and oxygen atoms there are present in a cup of water. So that was the exercise, and we're going to make use of this in this chapter and also in the succeeding chapters. So it's kind of like a domino effect. If you don't know one, you're probably going to have a difficulty in getting through this this courses chapters ahead of time. So don't worry. I'm hoping that you're already okay. If not, we'll try to troubleshoot it like I said, but it's really helpful if you're already there partially. So you just need to tweak it up a little bit instead of really massaging the whole and then fixing up the whole mess. Okay. So I hope you did your homework diligently. So we're going to talk about reactions. So we know the compounds, we know the symbols of the elements. We're going to figure out what would be produced if we're going to mix two of these in a reaction. Okay, so in the homework that I gave you guys, not really a homework, but the lecture on Tuesday, you've seen that there were different kinds of chemical reactions. We only resort to these 5 reactions, okay, for this course. Now, technically, this right here, acids and base, it actually belongs under the category of double displacement, but it's in its own story right there. So we know the combination because you have multiple reactants, and then when you put them together, they all fuse or combine to form one big and giant molecule. Okay, an example of this is when you're trying to build muscles or you're trying to build a tissue or something, creating something into your body. So we're going to get some carbons here, um, nitrogens here. We're going to create proteins, carbohydrates. We're going to fix it up and we're going to create, yes, it's recorded, into a bigger molecule. Then we have decomposition. Decomposition is definitely the reverse of combination, wherein you have one big chunk of molecule and you break it apart and you're going to form multiple individual many products. Okay, so it could be an element or it could still be a compound, but it's kind of like a breakdown, smaller chunks than the original big molecule that you started off with. So an example of that is when you're trying to break down the food that you eat and digest it so that you will break it into a smaller component so you could harvest the energy. So that's another example of that. Okay, and then we have combustion. Combustion is something that we know at the get-go because one of the reactants there is oxygen. In order to burn your fuel, you need oxygen to do that. So oxygen is one of the reactants in combustion, and usually the products of the reaction will be carbon dioxide and water. Now your fuel would be mainly be carbon and hydrogen, and that's why you have carbon dioxide and water, but it's also possible that your fuel can have oxygen in itself, nitrogen, and some sulfur. And if that is the case, when you're trying to burn or do combustion reactions, you usually not have just carbon dioxide and water only as your products. It's possible that you could have nitrous oxides and also some sulfur oxides in the byproduct. Okay, but for your course and for this class, we're only going to resort to fuels that contains pretty much carbon, hydrogen, and oxygen. And then you're going to form a product of carbon dioxide and water. If it is a complete combustion, you're assuming that you have enough oxygen there, or more than enough oxygen, to burn all of your fuel to have to fully convert it to carbon dioxide and water. And if it's an incomplete combustion, you don't have enough oxygen, what do you think will be the product if there's not enough oxygen to burn the fuel? Any guess, guys? Very good, Salil. So it's carbon monoxide. Okay, so when you don't have enough oxygen, you're going to create this side product called carbon monoxide. And that's the problem, because carbon monoxide can tend to adhere to some of your um, blood proteins. And in doing so, you're not going to be able to carry oxygen in the process. So it's you hear something like carbon monoxide poisoning, right? So you won't be able, your hemoglobin won't be able to carry the oxygen anymore, mainly because carbon monoxide is sitting there, okay? And it has definitely impede the process of the oxygen supply in your body. Okay, so we'll do some examples of combustion. We're gonna skip uh, combination and decomposition because it's somewhat easy. Let's just do a one problem, okay? Let's do one problem for each so that you'll see how that goes. Because sometimes I would give you a worded problem and you're going to be asked to balance the reaction. And of course, that would call on how your ability to be able to write the symbols of these elements and compounds that are used in the reaction. So let's try to do number one. Okay, so we have solid sodium reacting with chlorine gas in order to form sodium chloride. Notice there that I have made use of these subscripts in open and closed parentheses. Sometimes you would see that SLG and AQ. This is just to give you a description of what it looks like before the reaction and after the reaction. So S stands for solid, L refers to that substance is a liquid, G for gas, and when you have AQ as a symbol, that usually refers to that compound or or element for that matter is being dissolved in water. So it's in its aqueous form. Okay, so we have solid sodium, NaS, reacting to a chlorine gas, and if you remember, chlorine is one of those 7 elements that you need to have subscript 2 in there. Okay, so I would say casually chlorine. So please make sure to think that it is diatomic. Okay, so you always put 2 in there. And you're going to form a compound in the process, sodium chloride. I know that it's a compound because look at the ending of the name. It ends with IDE, right? So chloride is Cl negative, sodium is Na plus. So when you bring them together, the formula will be NaCl. Now notice that the number of atoms of these elements on the left side and the right side of the reaction, before and after the reaction, they have to be the same. Okay, so the rule that we apply is the law of mass of conservation. When we're putting something in to have the reaction happen, when we take that product out, it may no longer be the original um, atoms, but the number must be the same. Okay, the number has to be the same. You did not take out anything, you did not create or destroy anything. It has to remain intact. So if you look at sodium, sodium has the same number. It's still one atom, sodium atom. But if you look at chlorine versus the chloride in the salt, the number decreases, okay? Which means to tell me that in order to balance it out, I need to adjust the coefficient, okay, 2. By putting 2 in there, that implies that I produce 2 molecules of sodium chloride. So there's 2 chlorine atoms. 2 chlorine atoms on the left. They balance out. But when I put 2 in there, that also implies that there's 2 sodium. So now I have to adjust the number of sodium on the left side of the equation. So then I have to adjust the coefficients. Okay, by the way, for those who just came in, these numbers right here before your substance is referred to as coefficients. It tells you the number of substance you have. Okay, so you have 2 sodium reacting with 2 chlorine molecules. After the reaction, if you let the reaction proceed, it's going to form compounds, 2 molecules of sodium chloride. Okay, so in the beaker. So this is just a schematic representation of what it looks like if you were to look at it in a more picturesque kind of way. All right. All right. So notice that I could put 1 in here to indicate that there's 1 chlorine molecule. But in chemistry, when you have 1 of that particular substance, you don't have to write the number 1. It's just so messy. Plus, it's already implied that you have 1 chlorine molecule. So usually you don't need to write the subscript, the coefficient 1 in there because it's already implied. Okay. It's the same as you don't have to put the subscript 1 because it's already implied that you're dealing with 1 sodium atom and 1 chlorine atom in a molecule. All right. So now let's try to do some decomposition reactions. Okay, you see it's combination. You have 2 entities or substances. When you after the reaction, you only have one molecule or 1 substance. You may have 2 of those substances, but just 1 substance. All right, let's try to do the other one. Let's try to decompose water into elemental oxygen and hydrogen. If you hear about you can run your car using water, so that's this making use of this chemistry. So you have water right here, you zap it up with some sort of an electricity, and what's going to happen is it's going to break down into its elemental form. So you're going to have hydrogen gas and also oxygen gas. Remember, these elements are diatomic and they have to have the subscripts too. Okay, now when we have that, then all we need to do is introduce heat, and this will be our fuel. Hydrogen is reacted to oxygen and then it's going to combust. It's going to generate heat, and that heat is what drives our car to run. Okay, now notice that this right here is not balanced. The number of atoms on the left does not match with the number of atoms to the right. And so you need to do that by adjusting the coefficients of this number. Now, in practice, you've seen Tyler do it. Now, let me try to do it my style so that you can see how I do it systematically. Some students do this by eyeballing the coefficients, and that's fine for equations that are very, very easy. But let me show you a more systematic way of doing this. Okay, so we have here, once you put a number in, do not change the number in the mid-process. That's usually what I suggest to students when they're doing it for the first time. Okay, let me just put a box there to indicate that that's coefficient. Okay, so I usually would choose and look at, it doesn't have to be on the left side or the right side. I could start with the right side and put a number in there. But for this problem, I'm going to start with the left side, mainly because you have only 1 substance, and then you have there the most complicated structure, right? So water is more complicated than, say, hydrogen or oxygen. I'm going to assume my basis of calculation that I am dealing with 1 molecule of water, okay? And that means that I have 1 oxygen atom and 2 hydrogen atoms. Now, if I do it to the right side, in order to balance out the number of hydrogens and oxygen, let me just break this down into its elemental form. In order to match with the right side, the number of hydrogen on the right side must be 2. And in order to do that, the coefficient here must be 1. So 1 times 2 will give you 2, right? So now hydrogen is balanced. Now what is left now is the oxygen. On the left side of the equation, I only have 1 oxygen atom. So in order to balance it, on the right side, I need to have 1 as well. Now remember, oxygen here is diatomic. It already has a subscript 2. So we have subscript 2. I need to multiply it by half or a fraction, so that if I multiply it by 2, it will give me 1. Okay, and then just humor me here. I just put 1/2 here. That way, 1/2 times 2 will give me 1. And now my equation is all balanced. In theory, it is balanced, but there's no such thing as half of a molecule. And therefore, in order to get rid of that half, I need to multiply both sides of the equation by 2. And in doing so, the coefficients now has changed to 2, 2, 1. By multiplying both sides of the equation, I have got rid of the fraction. Okay, and now this is now my balanced equation. The main thing that you need to remember when you're balancing equation is that the coefficient has to be in whole numbers, because there's no such thing as half a person. Okay, it has to be a whole number. Number 2, the numbers there must be in its lowest form. Okay, so I can't have 4, 4, and 2, because I can still divide that by 2. It has to be the lowest form that you can no longer divide it or make it any more simpler. Okay, say the parenthesis next to water. Next to water, it says letter L for liquid. Liquid. Okay. All right. So this is relatively easy. You probably just eyeball this when you did this balancing of equation. So let's try to have a more complicated one, okay? We'll try to do combustion. So combustion of octane, you don't have to remember what octane is. Octane will have the formula C8H, C8, 16, 18, there, okay? So C8H18. This is the fuel, main composition of your gasoline. Okay, so let's try to burn octane fuel. So since this is combustion, again, trigger point there, the word combustion, you know that one of the reactants there has to be oxygen. The octane there is your fuel. When we're burning that, the products will be carbon dioxide and water. Okay, all right. Of these substances, I believe the octane, the fuel, is the most complicated molecule. And so I'm going to choose this as my basis of calculation. I'm going to put a number in here, 1. So I'm going to assume I'm going to burn 1 molecule of this fuel. That's what I'm trying to do. If I do that, then if I break this down, there's just going to be 8 carbon atoms and 18 hydrogen atoms right there. Okay, on the left side of the equation. Now notice that the oxygen here does not contain carbon or hydrogen. So oxygen is the molecule, or the gas is only comprised of oxygen element. Okay, so I'm going to try to then balance it to the other side of the equation. The number of carbons and hydrogen here on the right side must match with that of the left. There needs to have 8 carbon here, as well as 18 hydrogen atoms on the right side of the equation. So to do that, this coefficient here must be 8, so that if I distribute it to my molecule, it will have 8 carbon atoms. Okay, all right. So now we'll look at the water. What would be the coefficient then if we need to have 18? Perfect, 9. Okay, so 9 times 2 will give you 18. Now notice that the source of oxygen in this right side of the equation is from these two molecules, okay? When looking at carbon dioxide, that's 2 times 8. There's going to be 16 oxygen atoms there. And plus the oxygen in water, that's 9 times 1. That would be 9 for a total of 25 oxygen atoms. In order to balance that out, the number of oxygen atoms on the left side of the equation must also add up to 25. Now here, I have a diatomic oxygen. So what number would this be in order to give me 25? It will be 25 out of 2, correct? 25 over 2 multiplied by 2 will give me 25 oxygen atoms. Now again, once you have that and all of the numbers or all of the coefficients in the substances is already filled, that's when you stop. Now you then assess, is there a fraction? You have to get rid of that fraction. To get rid of that fraction, you have to multiply it, both sides of the equation, by that number. That's 2. So I'm going to get rid of that 2 by multiplying both sides of the equation by 2. So this becomes 2. 25 times 2 gives you 25. 8 times 2 will give you 16. 9 times 2 will give you 18. And this right here, guys, is now the balanced equation. For every 2 molecules of your fuel, you're going to need 25 molecules of oxygen gas in order to convert it all to 16 molecules of carbon dioxide and 18 molecules of water. Any questions? Okay, let's try to burn something. Okay, I'm going to do one more. Can we do one more? Let's do it. Okay, now I want you guys to burn this guy. When we have carbons, as it gets longer and longer, now notice methane is carbon, only one carbon. It contains one carbon and some hydrogens in it. The nature of it is gas, right? If you look at your propane tank, if you open the valve when you're trying to barbecue, that fuel is still gas. But when you go to the gas station, the gasoline, which has 8 carbons, it's liquid. And as you get bigger and bigger, you get more and more waxy. Okay, so here is another fuel, C25. It's actually now a solid state when you're trying to burn that. So that's C5H. Let's try to do 48. When you're burning that, predict the products. So you know that that's carbon dioxide and water. Let's try to balance this equation. Okay, so I'll give you a head start. Try to do that on your seats, guys. Has someone had the coefficient already? You said 1:37. I am not making an educated guess. So there is some formula to that. Okay. The naming of organic molecule. Okay, and we're not gonna get to that. If you guys are going to Chem 306 or taking an organic chemistry class, then you're gonna learn how to name these organic compounds. All right. So let's try to do this. Okay, so one of you said that the coefficients of fuel and oxygen is 1:37. Any other answer? If you guys have any, feel free to share. And let's try to do it. Okay, so I'm gonna, again, basis of calculation will be this one. You could choose um, you could choose not to use this fuel as your basis of calculation. You could get started with oxygen right away, but that's going to make it more complicated. But because on the other side of the equation, you have two sources of oxygen. So now you're going to start guessing, right? So I'm going to go with my fuel as my basis. I'm going to assume that there's 1 molecule of this fuel, which means that there's 25 carbons and 48 number of hydrogen atoms, which means to say that the number of carbon here must be 25 in order to balance out the number of carbons. Okay, now if you look at hydrogen, the only source of hydrogen is on the right side of the equation is that of water. In order to match it with 48, then I need to have the coefficient 24. Okay, 24 times 2 will give me 48 hydrogen atoms. Okay, now it seems to be balanced now. What's left is to balance oxygen. Now I'm going to do the right side first because now all of their coefficient has already been filled. The number of oxygen atoms on the right side is 25 times 2 from carbon dioxide. And the number of oxygen atoms on water is 24. 24 times 1. Okay, so that's 24 plus 50. That would give me 74. And I need to have 74 oxygen atoms here on the right side as well. So what would be that coefficient? If I'm going to multiply it by 2, it's going to give me 74. So this is now like an algebraic, I've just created there an algebraic equation, right? So x would therefore be 37, right? Times 2, right? I was hoping someone would like interject. 37, yes, 37 times 2 will give you 74. So correct. Thank you for the one who just answered that for me, okay? So you are correct. So now the only thing is just a final cleanup or work up of your balancing. So that will be C25H48 plus 37O2 will give you 25 carbon dioxide molecules and 24 water molecules. Notice that I got rid of the number 1 because it's already implied. Now your lab this week, you're going to be asked to balance some equations. If there's any substance there that has a coefficient 1, please erase it. Even if you have a box in there, just keep the box unanswered or leave it blank. Okay, to indicate that you have 1, it's already implied that you have 1 of that molecule. During the test, however, you might be asked to write the number 1. Okay, but for practice, whenever you're doing that, you don't have to write the number 1. It's already implied. Okay, is this clear, guys? Because I'm going to test you, okay? We're going to Kahoot this thing. Let's do a Kahoot game on balancing of equation. Now I'm going to move on to the other two because these other two is actually more important than anything. So we have here the double displacement reaction and the single replacement reaction. If we look at double displacement, the format contains 2 compounds, okay? The compounds usually contains a metal and a non-metal, right? So let me just put the letters A and B for the metals, reacting with non-metals X and Y. So you know it's a double displacement reaction or double replacement reaction because you have 2 compounds, compound 1 and compound 2. Now what this reaction usually does is that it changes its partners. Okay, so the metal here will react with the non-metal of the second compound in order to form a new product or a new compound, AY. And the metal of the second one will react with the non-metal X in order to form BX. So they just switch partners. Single replacement, by the word itself, there's only one that is being replaced. So that means you have one compound and an element right here. Okay, so one compound and an element. And what this does is it only replaces one. Okay, so this B will go with the X in order to form BX, displacing your A so that now your A is now the element. Okay, so there's only one that is being replaced in the compound, whereas double displacement, both of them, the metals and the non-metals, is being replaced. So we're going to start with double displacement first. I usually say double displacement. Some textbook will say double replacement. Some textbook will say double exchange. They all mean the same thing, okay? Because once we master this, it's actually easier to do the single replacement because there's only one replacement, or one of the component there is being replaced. So let me do that. Before we do that though, let's think of these compounds not as solid molecules. So when you say sodium chloride, don't think of them as the solid chloride crystals, but rather think of them as they are dissolved in water. They'll usually take place in aqueous solutions. So think of them as aqueous solution. When you look at sodium chloride, if you look at that Kahoot drawing there earlier, you see a bunch of sodium chloride. I can't believe why it's not here in this drawing, but it's actually a lattice. Okay, so you have sodium and chlorine, but your table salt actually contains billions and billions of these guys. And they're going to form somewhat of a lattice structure. And I don't know if you guys have seen that one. So let me just do a quick drawing here. All right, so it's going to appear like this. This is what your sodium chloride or table salt will look like if you look at it in the magnifying glass. Okay, so you have your sodium, which is the green sphere, interacting with the purple chlorine atoms, and then they basically get stacked because now in the other sodium chloride molecule, it's going to be attracted with the negative chlorine. So you can see that there's some interaction here happening. Okay, so kind of like magnets, they just rearrange themselves into these beautiful lattice structures. This is very, very strong, guys. Imagine trying to rip apart a magnet. They're actually very strong. It's hard to rip them apart. And so it's very, very hard to separate sodium chloride molecules apart. Imagine gasifying table salt. Don't do this at home because you're going to need more energy than just the heat from your stove. But if you put it in a frying pan, it will take a while before sodium chloride crystals gasify out. If you heat up your pan, your sodium chloride crystals will still remain in there as crystals, right? You're going to need more and more energy to break this apart into gas molecules. Okay. However, when you put table salt in water, it automatically breaks apart. Okay, you won't see the crystals anymore. What you see there are its ionized version. So whenever I talk about this reaction occurring in aqueous solutions, think of these compounds as split ions. Okay, there's still a 1:1 ratio of sodium ion and chloride ion in there, but they're separated. And why is that so? When you have sodium crystals so strong, how is it being ripped apart by water? Okay, so these are your water molecules. So water molecules look like this. Now, we will talk about this later, but the water molecule, if you look at the temperature profile of water molecule, there's some areas in water where the electrons will conglomerate, and that's usually around oxygen. And the electrons here in hydrogen will basically go towards oxygen. Okay, so it's heavier on that side. So you can see that usually denoted by the textbook as partially negative, and the area where there's no more electrons or negatively charged particles will be partially positive. Okay, so notice how they are surrounding your sodium ion. It's usually the oxygen that is oriented in, around, or closer to your sodium ion, is it not? Because the negative charge of water gets attracted to that positively charged sodium. You could also take a look at your chlorine. And if we focus on chlorine right here for a second, notice how with chlorine, what is surrounding it is still water molecules, but look at the how they are oriented. Hydrogen now is now conglomerating around chloride. And again, another sodium ion here. The oxygens are surrounding your sodium ions. Okay, so these millions and millions of water molecules rearrange themselves, and then we're able to pry and pull the sodium ion apart from the chloride ion. Okay, the strength is so strong enough that they're able to do that. We call this the hydration of your molecules. Okay, now depending on the compound, it will rip apart into several ions. Okay, so for a 1:1 ratio, like potassium chloride, you're going to have potassium ions and 1 chloride ions. Now, if you have other compounds like this, you're going to split it in apart, and the number of ions will also depend on that compound. So here we have potassium ion and our hydroxide polyatomic ion. Here we have sodium ions and sulfate ion. And so if you look at the subscript actually tells you how many ions there are involved. So there are 2 sodium ions that can be ripped apart from this compound and 1 group of sulfate ion. Okay, so if you look at water, if you drop 1 sodium sulfate molecule in water, how many entities are there? How many species will you see if you drop 1 molecule of sodium sulfate? Anyone care to shout out? Just shout it out. Don't put it on the chat box. 3. You have 2 sodium ions and 1 sulfate ion. Okay? So think of 1 molecule split into 3 ions. So there are actually 3 things. So the more complicated your molecule have, the more ions you can produce, right? So for ammonium chloride, you have 1 ammonium ion and 1 chloride ion. These polyatomic ions stays together. They won't separate into its elemental composition. They will stay together because of its nature. And we're going to get to those, okay? So here we have 2 sodium ion and this really weird stuff, we don't know, which has an overall charge of 2 minus, okay? So we're going to just write that out. One of that really weird group. We know that it's only one group because it doesn't have an open and close parenthesis. If there's a sub open and close parenthesis, then we know that there's more than one. Okay, very important, guys, when we deal with the next portion of our discussion. Okay, now since you have ions now in your solution, in your water, it's actually going to make your water susceptible to conduct electricity. Okay, so now you have formed an electrolyte solution. What is electrolyte solution? It means that you have some charged particles present in the water. And these charged particles can conduct electricity. Take a look at this drawing that I have here on the screen. You have 2 different setup. Okay, you have a beaker and you have here a source of battery, and then you have here, if you guys are aware of how electricity works, right, you're gonna need a battery, a simple battery, and then let me just do the orientation differently. I'm going to tap this in here, and then I'm going to have another wire. I'm going to tap it into my light bulb, okay? And then I'm going to close this wire. If it's a closed loop, then you would see that your light bulb will glow. If you take out this wire and open it up, it's not going to light up, okay? So let me open up my circuit for a bit. I'm going to open it up right here, maybe, and I'm going to dip it in a container, in a beaker that is filled with water. Oh, just plain beaker for now. Okay, because this circuit is closed, then your bulb is not going to glow. Okay, it's dark. If you pour water to it, it's still not going to light up. Okay, because the circuit is not closed. Now, if you put table salt in your water, so you're going to form seawater in there. Okay, the ions here, the positive and negative ions, now you're going to have ions present in your solution. The ions there act as a liquid wire that basically is able to grab those moving electrons and pass them around, okay, kind of like a relay. And because of that, your light bulb will glow. So if you put table salt or any sort of compounds that can break apart into ions in water, you're going to form an electrolyte solution which will make your light bulb glow. Whereas here, if you put a compound that does not break apart into ions, like covalent compounds, sugar, for instance, we know that it's covalent. How do we know that it's covalent? Because it contains non-metal group, including hydrogen, okay? So it's a non-metals. So it will not split apart into ions. So they would stay as sugar molecules. They would still be dissolved in water as sugar molecule. It will stay together. Because of that, it's not going to glow. Okay, so this is how they make use of this. They know diabetic person, they have more sugar in their bloodstream because they can't process the sugar. And so their electrostatic signal is quite different from a person who doesn't have diabetes. All right. So why are we talking about that? Because we need to know these terminologies. Who is a strong electrolyte and who is a non-electrolyte? So obviously, it is an electrolyte if you can form ions in the solution, okay? And it's considered non-electrolyte compound if it does not give you ions. And who are these guys? It's usually covalent compounds that will stay as a compound and they will not break apart into ions, okay? All right. If you're ionic compound or an acid, chances are you can break apart into ions, right? It's like sodium chloride, for instance, or your acid hydrochloric acid, okay? So chances are it can, and I said chances are because not all could. So only soluble ionic compounds and also, how do I, this, okay, let me see. Soluble ionic compounds as well as strong acids, they're the ones that will break apart into ions and therefore will make the solution electrolytic. If they completely break apart, then they're called strong electrolytes. Okay. Now what about those ionic compounds that does not break apart easily in water? We call them insoluble compounds, insoluble ionic compounds. And there's also some acids there called the weak acids that doesn't break apart easily. Because they only partially break apart, then they're called weak electrolytes. Okay. So now the next question is, what is the follow-up question? Who are these strong soluble ionic compounds and who are these insoluble ionic compounds? Well, to answer your question, the only way for you to know who is very soluble to water and who is not soluble to water is to go to the solubility chart. And you can see that in our formula sheet. So this is the formula sheet that you can see under modules essential data. So you will see this little portion right here on the right side. These are your solubility guideline chart. You're going to see that it's kind of split into two parts, right? So we have here the soluble ionic compounds and compounds that are insoluble to water. Okay, since it's already here, you don't have to memorize it, but I would recommend that you memorize at least a few of these so that you don't have to keep looking at this chart all the time, because time is of the essence, right? This is my worry to students, because in the on ground, I only give them this piece of paper to take the exam. For you guys, you have the whole world in your fingertips. And because you rely on it so much, you're like, I'm not going to memorize those. It's right here, right there. I'm just going to flip my notes. Well, time is of the essence in the exam. You probably will run out of time flipping through your notes if you don't know where they are. So it's a best practice to know where they are when you're taking the homework, exercises, so on and so forth. Have an idea where you will pull those information from. It's also important to memorize a few of these common rules, because time and time again, you'll be asked the same question anyway. So if you know it already by heart, you don't have to look at your formula sheet every single time. One of the rules there that I would like you guys to remember is this first two rules. Okay. If you're an acetate, any compound that contains acetate ion, so this is what we call the acetate ion. This could also be written as C2H3O2. Notice there's 2 carbon, 2 oxygen, and 3 hydrogen atoms in there with an overall charge of -1. So this is called the acetate ion. And NO3 minus. What is NO3 minus, guys? Do you recall what ion that is? Perfect. Nitrate ion. Nitrate ions and acetate ions, if your compound contains these polyatomic ions, they're automatically soluble to water. Okay? No exceptions whatsoever. Okay? No questions asked. Also, what you need to know is that if your compound contains metals belonging to this group 1, don't look at hydrogen here, but just these main ones that are colored in blue, as this makes your solution soluble to water. No questions asked, okay? So sodium chloride is an example. These group and also ammonium ions. All right. So try to remember that, because it's time and time again, it's just repetitive. Okay. Now there are some also compounds here that are soluble. So chlorides are soluble, except, see here, this second row, it is soluble to water. Sodium chloride is soluble to water, except when that chloride ion is combined with these heavy transition metals, silver, mercury, and lead ion. It will make the compound insoluble to water. So notice that there's some generalization and there's some exception to those rules, right? So whenever you're doing this, keep this in mind that there are some exceptions to the rules. Now, there's also some compounds that are insoluble to water, and these are these guys. So notice sulfides are insoluble. Carbonates, like if you go to the mountains and you will see these white colored mountains, that's not snow, but they are made of rocks that are made of limestone. That makes the color white. Okay, so these are calcium carbonate minerals. There's some rocks there that are made of phosphates. Okay, so they're phosphates. And there again, here you see that the exception to the rule, unless if it's combined with group 1A metals or ammonium, then it makes it soluble. Okay, so the first rule would always be if it belongs to group 1A, it's automatically soluble. Okay. So why did I say about the rocks? Because if it would be soluble when it rains, then we won't have any more hills. Okay, so most of our stones are made up of calcium carbonates and some sort of phosphates. That's why it still stays there. Okay, so let's try to go over and predict whether it's a strong electrolyte or not. But I did mention here, strong acids are also strong electrolytes, but weak acids are not. So now what's the follow-up question? What are strong acids and what are weak acids, right? We're going to talk more in depth about acids, but we're going to introduce acids a little bit in this chapter. Strong acids, because why is it strong? Because it can lift a lot of weights? No, it's called strong because it's of its ability. It has the ability to completely ionize into water. So if you have hydrochloric acid, if you drop it in water, it will break apart completely into its ionized form. Whereas if you have a weak acid, for instance, your acetic acid, HC2H3O2. Remember, this C2H3O2 is your acetate ion. If you combine it with hydrogen, you're going to form an acid. And because it ends with ATE, it becomes ic acid, right? So acetic acid. This is the main composition of your vinegar. So if you put vinegar in water, what it looks like if you have a molecular magnifying glass, what it would look like is that if you drop in 100 molecules of water, only 2 of those molecules split apart into hydrogen ions and acetate ions. The remaining 98 molecules that you have dropped in there will stay as a compound. So you're going to have 98 of these compound form and only 2 hydrogen ions and 2 acetate ions in there. And we're going to talk about more about these guys in details. Okay, because it doesn't completely ionize itself to water, it only partially ionizes, then it's going to be called weak acids. There's a lot and gazillions and millions of weak acids. You don't have to memorize that, but there's only 7 strong acids in the world. And so you can memorize the strong acid or put that in a safe corner or in a safe area. Okay, usually it's these guys. Okay, binary acids, HCl, HBr, HI, and these polyatomic acids right here. So let's take a look at the periodic table so that it's easier for us to remember. HCl, HBr, HR are strong acids. The polyatomic ion nitric acid is also strong. Sulfuric acid is also strong. Okay, and then the group version. So we have 1, 2, 3, 4, 5, HClO3 and HClO4. Chloric acid and perchloric acids are also strong. Okay, so list them up, put that on a safe corner or safe spot so that you can refer to them in case you're going to be asked which of the following is a strong acid or a weak acid. It's going to be HNO3, H2SO4, goodness. And then it's going to be very, very thick. HClO3, HClO4, HCl, HBr, and HI. Okay, so 1, 2, 3, 4, 5, 6, 7. These are the strong acids. There's also strong bases, and that's usually belonging to group 1A and group 2A. Oopsie. Any questions, guys? A lot to take in. If there are strong acids, there's also has to be a strong base, right? So these are the strong bases, and they're usually group 1 metal. So sodium hydroxide, lithium hydroxide, so on and so forth. These are the list. And the definition of a strong base is that when you put it in water, it will break apart into ions. So don't worry much about these strong bases or strong acids. We're going to repeat them again. What I do want to emphasize is that at least I hope by now you know what is defined to be a strong electrolyte versus a non-electrolyte. Strong electrolyte means it can conduct electricity. Okay? Non-electrolyte means it can't conduct an electricity. Okay? And put this somewhere, guys. This notes. It's really good to have in case you're going to be asked whether it's an electrolyte or not. Okay? So let's try to test you guys a little bit. Here, this is also another solubility chart. And I believe I got this from the McMurray textbook. Okay, so look at this and compare it to the one that I give you in the formula sheet and see if there's any wrong or not included in that formula sheet so that I can upgrade it. Okay,